Thank you. I'm Kaisa.
I'm Kincaid.
And I'm Clayton Johnson.
And this is our project on detecting exoplanets using variable star photometry and the transit method.
And we were under the guidance of Dr. Richard Dietz.
To begin, what is an exoplanet? An exoplanet is a planet outside of our solar system orbiting some other star out there. And that star is a variable star, due to the fact that the planet is passing in front of it, causing it to change in brightness. A variable star is just one of those stars that changes in brightness, not always due to a planet orbiting it, but for our study, that was the reason. What is photometry? Photometry is a tool that you use to measure the change in brightness, and you can use it for stars, other celestial objects. In this case, we will be using it for a particular star. This is important to do studies on exoplanets because you can compare them to our planet and our star and solar system, but also you can learn more about our universe, which is our primary goal.
The technology that we are using involves a program online called VPHO, which is a photometric tool which allows us to capture the magnitude, which you just explained. And most of the stuff that we use is on the internet. So we use a website called iTelescope, which allows us to look at several telescopes that we can capture images with around the world. Here is an image of the telescope that we used in California. And here's an image of the SkyCam that we can view before we take an image. That way we know if there's clouds above or not.
All right, so the extrasolar planet that we were studying is called Trace 3b, and it is in the constellation Hercules, which is right there. And it was discovered in 2007, and it orbits the star Trace 3. And then what is a transit? So this right here is a lovely video of a transit. So as you can see, the extrasolar planet is traveling in front of the variable star, causing a dip in the magnitude or the brightness. Now you may be wondering, what's that second dip there? So as the extrasolar planet is traveling around the variable star, it's reflecting the light back towards us. So when it goes behind the star, then that reflected brightness isn't apparent any longer, and that's causing that to be the exact magnitude of the variable star. And then we know when these will occur because we've studied them, and we have very accurate predictions as to when these transits will occur. And additionally, using our Stargazer's almanac right here, we can determine when things will be in the best position in the sky. And we do this using the coordinates right ascension and declination. Now right ascension is measured using hours, minutes, and seconds. And then declination is degrees, arc minutes, and arc seconds. And these are based off the celestial equatorial coordinate system, which resembles our geographic coordinate system on Earth quite nicely, because it is essentially like a model of the globe, except it has an infinite radius. So it's a much larger scale model of just similar to latitude and longitude that we have here on Earth.
At the beginning of our procedure, we start with the home page of iTelescope, where we can look at all of these telescopes across the world. We can access telescopes in California, New Mexico, Spain, and Australia, which allows us to view many different stars and constellations, which is very useful, especially when you're looking for stars and constellations. So on this front page, we can get information from the telescopes and access the telescopes for imaging. We can look at the sky cameras for the weather, which is very useful, because if there are clouds above or a hurricane passing through, for example, the images will not be very good at all. And here we have a map of the Earth, which tells us what part of the Earth is in day and what part of the Earth is at night, which is very useful, because if you are nighttime here and you want to take a picture with a telescope in Spain, you're going to have a bad day.
So this is our actual process where we put in the information so we can take the image. On this side, you will see that we have a single image, and on this side, this is the image series. In the first box at the top, that is where you put in your image name. Ours was Trace 3b. Underneath that, you'll put in the right ascension. Like Julia was saying earlier, it's kind of our longitude and latitude, so these are the coordinates that we will be putting in. Our right ascension was 17.8686 hours. Underneath that, you put your declination, which is also another coordinate, and it was 37.541 degrees. Under there, you will see there are a few more boxes. The first box, you put your duration in seconds, and we mostly use 180-second durations of exposure time. And then beside that is your filter. We used a V filter because we did not want to take color photos. We just wanted a black and white photo. Any filter that you use will take black and white photos, but later on you can put them onto a computer system and use contrast and saturation to add color. Next to that, you put your binding and set it at 1 and then acquire image. For a series of images, you do the same thing, except you can put in your count. So if you'd like to take 5 180-second exposure photos, then you just put a 5, and then so on and so forth.
All right, so after you decide that you want to acquire the image and click the button that specifically says Acquire Image, you will be redirected to this screen that says System Status. Now this box is the system status of a telescope that we used when it was not in use, but this is the system status box of a telescope that is currently in use. So what basically it gives you is it gives you the information that you entered into the telescope up at the top with a few extra little bits of information. But what you mainly want to pay attention to is the bottom box that says current running script output. So what you're going to see in there is it's going to be spitting out information as to exactly what the telescope is doing at the moment. So it'll let you know if it's focusing or if it's changing your coordinates or whatnot. And it'll tell you if something is going wrong or if someone is interfering with your photos so that you can easily detect what the problem was if there was a problem with your image.
After you take an image, we upload the image or images that we received to VPHO, which is the photometry tool we explained earlier. Here we can see a list of images, and we have 21 images in this image of the website. And each row is one image. So you can see certain characteristics of each image, such as the telescope used, the name, which is for our organization only. The computer is not smart enough to know where everything is. The date and time the image was taken in universal time, which is not fun to use. Air mass, which is the distance relatively between the ground and space, and we try to keep that as low as possible. The exposure time, and the sort of filter that was used.
This photo on your left is what you will see when you click on one of those images. Originally, when we take the image, the sky is black and we have pretty white stars, but we invert it to save ink and to make it easy to identify black spots on a white page. If you look, there is a star with a green circle around it. That is our target star. There are also a few stars with some blue circles around it, and those are comparison stars. Originally, we just used one comparison star, because what we do with comparison stars is we know their magnitude, so we compare it to the magnitude of our target star to compare its accuracy. To make it more accurate, we also use a check star, which has the same purpose of a comparison star. And we use 130 and 139 as a comparison and check star. Over on the box on that left image, you'll see it says S and R, and that's signal to noise ratio. So the less noise you have, the better signal you will get, and that's what we want. So the bigger the number, the better. On this side, you'll see that we have another image, and that has to do with pixels and saturation. So each one of those boxes is a pixel. Within each pixels are photons. And you do not want a saturated photo because that means you got too much light in the picture and you can't use that photo because it's just not accurate. So if you have a pixel with over 60,000 photons within it, you can't use it because it's saturated. You want to shoot for anything with 40,000 photons or below, and usually what we got was about 25,000 as an average of photons per pixel, so that was great.
All right, so then after you view that, you can click the button that says View Photometry Report, and this screen will come up, and so essentially it gives you the information that you put into the telescope about your image. And then at the top, it's going to give you your magnitude, your error, your standard deviation, your signal-to-noise ratio, a lot of important information. Now, these stars at the bottom, those are your comparison stars, and those are also playing a very important role as to the numbers in the top boxes that are what we're looking for. So if you see these red boxes around the comparison star magnitudes, that means that there's a high error in those magnitudes of those comparison stars. So you're going to want to get rid of those comparison stars and uncheck those boxes so that you're getting a more accurate magnitude and a lower error.
Now, what we did with the results that we got, we had the magnitude and we put them into a table in Excel and turned it into a graph. Now, the graph represents over time the change in magnitude, and we have the x-axis flipped. That way it shows the decrease in brightness instead of the increase of magnitude. So here we have all the data points fairly straight and stagnant. They don't really deviate from that line too much, which is good because those images were taken before the transit even begun. So if there was much flux in the data points, that would be bad. Here we have it when the planet is starting to move in front of the star, which slowly decreases the brightness. And then after that, we have it straighten out again, which is when the planet is directly in front of the star from our perspective, blocking the most amount of light that it will. Here we see exactly the same thing, except with a different number of comparison stars. As you can see, it's relatively the same, and there's not much deviation from the previous one.
So, our results. The accepted value that we wanted was 0.029 change in magnitude, and what we got was a change of 0.027. So we can say that we were successful in detecting exoplanets with these technologies. So we can also say that this technology works properly in doing so.
All right, we were successful, and that means you can be too. Amateur and expert exoplanet detection is a very up-and-coming field, and it's very intriguing and integral to space exploration. There is a recent discovery of a planet called Kepler-22b, and that's an exoplanet that resides in the habitable zone of its sun, and it's 600 years away from Earth. And what this means is it is in a place relative to its sun where life could potentially be found. The surface temperature of this planet is reckoned to be about 70 degrees, and although they're unsure as to whether the surface is made of gas, rock, or liquid, it's a very exciting discovery, and this field is very interesting and has a lot to offer.
Here's our works cited, which is lengthy.
And then we'd like to thank our sponsors. Mine was Ball Aerospace Corporation.
Mine was Noble Energy.
And mine was the F. Chorus Foundation.
We'd additionally like to thank our research sponsors. Mine was the Xcel Energy Foundation.
Mine was Noble Energy.
Mine was the Bacon Family Foundation.
We'd also like to give a big thank you to our mentor, Dr. Richard Dietz, who guided us through this research and assisted us and made everything go really smoothly and was a great force.
I would also like to thank our advisor, Maurice Woods III, who helped us complete all of the tasks that we were assigned, such as write the paper and meet these deadlines, which were very important because they were certainly not easy to get to most of the time. And he's been doing a very good job of keeping us on top of that. So thank you.
And we'd also like to thank Lori Ball and the FSI staff, Christopher, Jessica, Sean, Amy, Maurice, as well as our friends and family. I'd like to make a shout out to my New York family, Zach Burka and Hayes McCracken. Zach, the shirt fits great. Thank you.